Well, hello, everybody. My name is Jim Hoke, and I work for Parker Hannifin Corporation. I've been with Parker now since, 1992. I think I started with them. I'm a mechanical engineer. I'm home officed out of Tucson, Arizona, and I started with Parker as an ME, a mechanical engineer, coming out of University of Cincinnati. So I've been with Parker for a long, long time, held a lot of different roles within Parker. Parker formed a market-facing team back in 2009, originally called the Power Generation Team, and we've since changed that name to the Parker Energy Team. So I've been a part of that team for the last 11 years, and really my whole role for Parker is to develop business in the power generation space. So I've been around the electric generation market now for quite a while, and a lot of the mechanical subsystems that are in the plants. And what I wanted to talk about today was a particular product that Parker has both acquired and developed, I guess maybe is the best way to say it. It's a Parker Abex, ABEX brand of electrohydraulic servo valve called Jet Pipe, registered trademark called Jet Pipe. And that valve in power applications is really for electrohydraulic control of either gas or steam or guide vane, a lot of different control functions within the plants. And the topic of the presentation that I have is reduction of maintenance concerns and the associated costs with gas turbine fuel control valves. So this is a little bit of a case study and application information on those electrohydraulic servos. I wanted to give a little bit of history on Parker, how they developed in the aircraft and the aerospace industry. I think it sheds a little bit of light as to who we are and why we're where we're at today. This is something that I get a little jazzed about, being a mechanical engineer. I really like the history of both the aircraft industry and then the aerospace industry as it developed. So Parker started off back in Ohio. I grew up in southern Ohio. Parker's up in Cleveland, has always been up in Cleveland, their corporate headquarters, but the company started in 1917, and it was started by a gentleman named Arthur Parker. So he founded what was called the Parker Appliance Company, and the pin in the upper right-hand corner of the presentation is one of the original Parker logos. And I think that logo kind of evolved as Parker became more and more involved in the aviation industry. They stuck some wings on the Parker Appliance Company logo. So I think, love to have one of those. I've never been able to find one, but that's a piece of our company history. When the company was first founded, they really focused on automotive braking systems. And one of the things that Arthur Parker found was, as the auto industry evolved and the cars got faster, the trucks got bigger, could carry more payload, the brakes didn't keep pace with development. So one of the first products that Parker came out with was pneumatic braking components. So that was really kind of the essence, the beginning of our company was brake system products. And we make a lot of fluid transfer fittings and valves. At least initially, it was mostly fittings and valves for tubing systems. So Cleveland was pretty unique at the time as well. Big industrial city, was really, really entrenched in the beginning of the aviation markets, the companies that were building aircraft at the time. And kind of the neat part of the history that we have is that Parker had a relationship with Glenn L. Martin, who was one of the the innovators building aircraft, was heavily involved in World War I, and our only customer back in 1919 was Glenn L. Martin. So the history that I've been told is that the relationship with Glenn Martin led to introductions to the other beginning aircraft companies. So that would have been Wright Brothers, Donald Douglas, Glenn Curtiss. So there was, there was a lot of crosstalk at the time, and Parker was introduced to those companies and actually supplied them products as well. And then I also put a little picture here on the right-hand side. That's a Thompson Trophy. Back in the day when they were really, Cleveland was holding what they called the National Air Races, and that was to develop new technology in the aircraft industry and to showcase that technology. So that was a trophy that was given out during those air races in that 20-year period. And then here's a really neat part of our history in aviation. Charles Lindbergh's Spirit of St. Louis. I think this was Ryan Aviation that was out of San Diego. Parker was contacted to help build the fuel system or supply components for the fuel system on Lindbergh's plane. And that still gives me a little bit of goosebumps today. This plane's hanging in the Smithsonian. There were 5 tanks on that plane, 450 gallons, 451 gallons of fuel. So it was a flying gas tank, and that's what got his butt across the ocean, for the first time. So that's a really, really neat part of something that we were involved with through our history. So you can see our valves and fittings in there. And then, we were heavily involved in World War II. Our company almost went bankrupt after the end of World War II because all of our orders stopped. Our sole customer after World War II, our customer during World War II was the U.S. government. So a lot of the flight controls, fuel delivery systems, braking systems on the military aircraft were Parker components. And, as the industry continued to evolve and turbines were built and then the rocket program started, Parker was, NASA came out of Cleveland. So Parker followed NASA down into Huntsville, Alabama. We were involved with the, I don't know how to say it, the kind of the payload carrying rockets that the government developed with the Mercury and the Gemini and the Apollo programs. So we were hand in hand with the development of a lot of the control systems that went into the aerospace industry. So propellant control, hydrogen, liquid oxygen for crew oxygen, and then helium for thruster. So there's a little graphic at the bottom of this slide that shows a lot of the different check valves and control valves and manifolding and seals and fittings and all the different plumbing components that we had that went onto those vehicles. And then hopefully this will play.
Houston, the Challenger has landed. Roger, Challenger, that's super. Okay, Parker valve. Boy, you bet it is, Gordo. Oh, you said shut down. I shut down and we dropped, didn't we? Yes, sir.
So that was a little sound clip. Hopefully that came through fairly well. That was Apollo 17 landing on the moon. So that was the last manned vehicle that landed on the moon December 11th of 72. So that Parker valve was a thruster valve that they cycle to make sure that it's actually off. So that's just a little clip of our involvement with space exploration. Oops, excuse me. Go to the next slide here. So what I wanted to do now was do a case study. So this is an application story about our electrohydraulic servo valves that went into one of the 7F plants, 7FA plants. What we had seen through the years is as the engines evolved and became larger, the gas turbines, firing temps went up, the oils were used, the control oil and the lube oils were used a lot more. They were stressed quite a bit more. And one of the problems that came out of this was on the 7Fs in particular, they had a common lube oil and control oil tank. So they had a 6,000 gallon tank. It was an auxiliary skid called an A160, and the gas control valves were in that skid. So all of that electrohydraulic control oil was used to control either gas, liquid fuel, inlet guide vane, or as a stop ratio valve. And what the plants were finding is that they were having a lot of failures or a lot of maintenance issues with those an initial OE install servo valves. Not a fault of the servo, but it's more of contamination issues. So Moog servos were installed. GE used a lot of Moog components on their control valves, and in this particular instance, this is Marcus Hook Energy Center. It's a Florida Power and Light, was a Florida Power and Light plant, and this was a 3-on-1 facility, 3 gas turbines, 3 Hercigs, and then 1 steam turbine downstream, I believe. So these were 7F8.03s. Those engines traditionally ran about 6,200 hours per year, and the GE life expectancy on the OE Moog servos, or servos in general, was supposed to be 32,000 hours. So that's 5 years worth of runtime. And what the plant was seeing is that those valves, those servo valves, they were actually starting to see issues after 3,100 hours. So every 6 months, those valves were starting to lose their performance. And so what the plant was doing to ensure that the turbines kept running was they would pull those valves every outage. They would replace them with either new or rebuilt, recalibrated valves, and then send the old valves out for clean check test. And if they could be repaired, they'd put them back on the shelf. So here's a picture of one of the gas control valves with a Parker valve being installed, the red label tag on the servo. That servo valve that we have is it's a little bit different than the Moog. The servo valves are a 2-stage valve. The primary stage is an electrical stage, so it's basically an electrical signal comes into the valve. That signal controls a hydraulic pressure, call it an orifice. In our case, it's jet pipe. Controls the movement of that hydraulic pressure port in the valve, and then that in turn controls the second stage. It puts hydraulic pressure onto either end of a spool piece, and that spool piece shifts left or right, and that sends hydraulic pressure downstream, which would in turn move an actuator, and that actuator is going to open or close a gas valve or move an IGV, inlet guide vane. Just that's where you get your electrical to mechanical transition. So Marcus Hook decided, hey, let's put these valves on test. Let's put some Parker valves on test. So we installed 12 servos, 4 per engine. So I want to say that this was this turbine had a quat valve, so this was a primary, secondary, tertiary, and quaternary gas control valves. So we put 4 valves on each gas turbine at Marcus Hook. And as you can see from this picture, this is what the oil looked like at that plant at that time. So there was a lot of contamination issues with their control oil circuits. And one of the things that happens, it's not just particulate, there's also varnish formation. So as the oil breaks down, acids form in the oil, water gets into the oil is going to degrade and actually form varnish, which is going to, it's a kind of a thin, sticky, gold-colored deposit that's going to go onto the tubing walls, onto valving, into manifolds. And of course, servo valves have a very, very small orifice. Our jet pipe orifice is, I believe, an 8,000th diameter ID orifice. And the Moog valves are smaller than that. I want to say they're in the 3,000 or 4,000 range. So any kind of particulate could potentially plug that orifice. And then as you have varnish builds up in the system, the spool piece in the second stage, that spool piece is a very, very close tolerance spool, so you don't get leakage past the spool within the sleeve. And varnish starts to form, and that spool piece will begin to stick. So you send an electrical signal to the valve's supposed to move X amount. If the spool is sticky, the valve won't move, or won't move as it's supposed to move, so there'll be a little bit of drift there. GE recognized that, and they published a technical information letter, 1528, and that said, varnish, lube oil varnish is impacting reliability on these turbines, and the electrohydraulic servo valves could become sluggish or inoperable, and which could cause a trip, could cause the turbine to shut down. So our servo valves went in due to their contamination tolerance, better contamination handling. And then also on our valves, the way that valve is designed, our servo jet pipe, if it does fail, so if you get a particulate piece that plugs up that 8,000 orifice, that valve won't go full open or full close, which means if the servo fails full left or right, open close, whatever you want to call it, the downstream actuator would go full open or full close. Our valves won't fail that way. It'll either fail exactly where it was at when it plugs, or there could be a bias spring that's put into the valve that will cause that valve to close or open, whatever the design need would be. So that gives you some trip resistance through the use of a Parker jet pipe servo. After 19,000 fired hours, it was decided, let's pull one of these valves off, let's take a look, let's open it up, see how it's performing. They hadn't had any trips, no issues with any of the 12 valves up to that time. That was a total of 520 starts amongst the turbines, 3 years of operation with no issues. And then, as you can see here, this was serial number 9 that was pulled. So this valve was pulled off of gas control valve, and it was sent back into our factory. And when they tested that valve, it came out matching what our new performance requirements were. So the specs that we have per GE on how that valve is supposed to perform, new out of the box, the valve that had run for 19,000 hours in 3 years and 520 starts, it matched those performance requirements. So we took that as a thumb up that, hey, this valve's working even in that dirty oil environment, which we thought was pretty amazing. And in the interim, the Moog valves that had been installed, some of those valves had to be serviced up to 6 times. So there's quite a bit of changeover on the other Moogs, and I believe those would have been either IGV or stop ratio valves. So here's a picture of the jet pipe on the fuel control. As of 2019, December of 19, there were 60,000 run hours on that plant, and none of those valves had failed. So our valves, they're running. I don't know if they're still on those engines, but as of 19, they had been running continuously. And then, the big benefit that we see, and you may see it different here on the plant side, but the big benefit would be maintenance cost. Just the time and effort cost it would take to pull valves, either every outage, every other outage, whatever it is, buying new valves. So you're saving that cost. And then also, if you don't have to worry about trips, plant availability's increased, and then you're able to produce electricity and sell it. So that's what the plants are for. Here's a little close-up of the valve. Here's the primary stage where the electrical signal comes in. There's basically an L-shaped jet pipe. There's a piece of tubing in here that sits inside of a coil. As the electrical signal changes, that coil causes that piece of tubing to move. And then basically that hydraulic flow that comes through that 8,000 orifice tubing hits a pyramid-shaped or triangular-shaped pressure diverter, and it would divert the pressure either to the left side of the spool or the right side of the spool, pushing the spool in either direction. So that's how the valve works, electrical to mechanical control. The division from Parker that makes this is called Control Systems Division. It's part of our Aerospace group. And they're based in Dublin, Georgia. That's where all these valves are built and calibrated. And then also we do maintenance and repair. We'll do rebuilds out of that facility as well. Our valves are approved by GE on their 312A 6077 spec. And then we also have a long-term agreement with GE to supply them valves that would go into the aftermarket. None of these valves are going on new installs. The gas turbines today are actually using full electric actuation of control. Try to get the hydraulics. They try to get the hydraulics out of their packages now. So these are 7E, 7F, maybe even some of the Frame 6 series turbines. Valve's 100 micron contamination tolerant, and then it's a drop-in. So basically the hydraulic platform, the porting is the same as the Moogs. The electrical connections, the leads, are the same as the Moogs. And then the valves are matched up based on the pressure and flow requirements that are needed for each application. And we're really only looking at the 7Fs right now, but these also apply to any of the steam turbines. So for you guys that have GE steam turbines downstream, D11s in particular, these valves were actually original install on a lot of the steam turbines that GE built through the years. And then here's a little information on the GE spec itself. So we've called this the forever war internally, and reason being is that we had a chance to capture a lot of this market back in the day, but we didn't. We missed it. Moog got it. I think they had a less expensive product, and GE went that route. So we've always been campaigning with GE. Please add us to spec, so that the plants have some confidence that our valves were directly applicable to the Moogs that they have today. And what GE's finally done is they've recognized that most plants with no contamination issues aren't going to have any problems with the Moogs. But if you have oil issues, contamination issues, Parker valves are being offered as a severe duty alternative to the Moog. And what you're seeing here would be, this list would be all of the GE part numbers for the Moog valves, 1 through 10, for gas turbine applications. And then these part numbers from GE directly correlate with the Moog. So basically, if you have a Moog 312A6077P001, that would correlate with same valve P0043, which would get a Parker valve. But GE was looking at this as they wanted to offer that into the maintenance and repair market as a severe duty option. And we have full certification qualification. So these valves, I believe these valves can go even into the 50 hertz fleet internationally if you guys have any of those engines. And then a little bit of information on the Moogs. So here's a nameplate on one of the Moogs, a P006. This is a stop ratio valve. So again, here's the GE part number for the Moog. Here's the Moog internal number, G772K241A, and the corresponding Parker number from GE, the 0048. And then this is just an internal Parker number for us of our internal part numbering 447400-1001. So there's the crossover for that, again, stop ratio. And then this valve is P001. If you see, there are two different GE drawing numbers here, 312 and the 381. The 312 is the 60 hertz application, and the 3881 is the 50 hertz application. And again, crossover from Moog part number, GE part number for Moog, and over to the Parker side. One thing on that too, if I can go back. One of the things that we've been hearing from the field as well, from the plants, is that we believe Moog made a change on manufacturing, so they've gone offshore. They've gone into the Philippines for build, and there may be some quality issues there. Don't really know. Personal experience on your side, but our valves are made here, U.S., Dublin, Georgia. And then some of the applications, I believe we've got some valves on some of the frame 6s. I don't know about the frame 5, but the predominant fleet that we're looking at would be 7E, 7F, hence this presentation for the 7F Users Conference. And again, what we're looking at would be control valve actuation. So whether it's natural gas fuel or liquid fuel, stop ratio valve, and IGV, I don't believe we have a full offering for all of the IGV applications. In particular, the 7F 2.6s, I don't think, 7FA 2.6s, I don't think we have IGV for that engine. But we have a large variety of part numbers for both steam turbine and gas turbine applications. give you my email at the end of this. If you have any questions at all, if you want us to do some deeper research and see if we match up with what you have, I'd be happy to do that. The main build timing on these turbines would have been from the 80s up through 2012, and the bulk of the fleet, and I'll show you a graphic on this, the bulk of the fleet would be the 7Fs that were built. That was a really, really successful engine for GE. Multiple fuel types, and then, like I said, multiple iterations, because these engines really, and I'm not an expert here, but they've evolved. They came out with a base unit, and then they DLN, and then they did a 2.1, and on and on and on. So these many different iterations of these engines. So here's GE internal document for DLN and the development phases, and not a lot to go through here, but basically DLN-1 back in '91 when it came out, the simplicity of the fuel system on this engine, stop ratio valve, gas control valve. Parker actually makes the splitter valves, so on dual fuel applications you're going to see an isolation valve and a fuel splitter. A lot of the 7Es I think had this, but we do those large, it's not a servo valve, it's more of a mechanical hydraulic or liquid fuel type valve control. So we do those. Here's DLN2 from '93. So these are F-class machines, and you can see the complexity is growing to the combustor cans. So primary, secondary, and tertiary, third. So first, second, third stage, and then quaternary valve for fourth stage. And then up to '96, 7FA.2.6. DLN application here, and again a little bit more complex, but how we match up with G part number Parker 0048, and then the Moog number 006. And we do not have, as shown in red, I know in particular on this engine 7FA.2.6, we do not have IGV for that engine. And then here's a stop ratio picture. So stop ratio actuator. Here is a Moog servo installed. And then one thing on this as well, you're going to see in some applications Parker has some of the filtration or could do some of the filter elements that are used for gas control valves, lube oil skid, EHC circuits. We're a big filtration company as well. And then here's the graphic that kind of shows the build phases. So starting out with 7E back in the 70s, 38 count with the blue pins. And then in the 80s, it grew to 64 installs in the 80s. And that, I don't know if that was transition 7E to 7F, definitely in the 90s or the 7Fs. 90s, things started to skyrocket with 7F installs. And then 2000s, things went vertical. So, tons of 7Fs that were installed in the 2000s. And then things are starting to dwindle off in the 2010s. And, now everything's transitioning. Most of it's transitioning to H-class or J-class machines, the bigger turbines. And this is from Industrial Info Resources database that we use. And then, I don't know if this really applies, but basically we're looking at 32,000 fired hours. It's about a 5-year life expectancy. So we looked at, when the engines were actually commissioned, and then 5 years afterwards, we're looking at valve set changeouts. So we've tried to do some estimations as to the quantities that we would see that would require replacement after 5 years, 6 years of use. GE is, of course, trying to service their aftermarket that they have a long-term agreement with, some of the plants where they're doing service agreements. So the blue bar basically shows the count of the engines that are still under GTLTA, and then the red bar would be Parker's opportunity for Moog valve replacements in the field, and then total valve counts. So as of this year, we think there's probably 1,500 valves that would be cycled out of service in 2020. And then I guess the last thing I wanted to say was we have a website for our jet pipe servos. It gives you a better understanding of what that valve looks like internally, how it functions, how it was designed, what its strengths are. And I guess one thing I forgot to say was You know, the primary stage of our valve as compared to the Moog valve is different. We have a single orifice jet pipe style. Moog has a 4-orifice flapper style. But to me, the secondary stage is basically the same. It's a hydraulic spool. And what I was always curious about is in a varnish environment, if that spool starts to varnish up and stick, why does our spool move better, longer, than when a Moog valve does? And I think what we've determined is that they're actually, by the design of the second stage, we're putting more, I won't say more pressure, but there's more force being applied to the ends of the spool, which we call chip shear. And that gives that valve, that spool piece, the ability to move if it does get a piece of particulate in there, or if varnish does start to build and that valve becomes sticky, the spool becomes sticky. So the second stage design of our valve and potentially the tolerances on that valve enable that valve to continue moving as it lives, as it lives in the real world. So this website is available. The link is super long. So what I wanted to do is, if you have interest in seeing more about that, please send me an email, jhoke@parker.com, and I'd be happy to send you a link back. And then if you have any questions, specific questions about our valves and how they work, be happy to either answer that myself or get you back in touch with one of our product engineers. And appreciate your time, and thank you very much. Hope to hear from you. Thanks. Goodbye.